All right, so I'm gonna slowly get started here. There's a bit of a hiccup with YouTube for a second there, right when I was starting, um, saying that the streaming services were down, and it came right back up. So I'm gonna try to keep monitoring the health of the chat off in the corner there. Um, Warning: we have had strange people jumping into chat um, twice now in one in was that I think Tuesday's class. So you might see me pause for a bit while I block people that are asking, just trying to disrupt the chat. But it shouldn't be too bad. That said, we'll get started. We had kind of ended with, well, let me just do a look see over here, make sure we're in the same thing. I've been sending emails out with when things are due. I'm trying to do that on the T days, Tuesdays and Thursdays. I have been finding getting material up on Blackboard and then replicating it across the 4 sections takes an age. And the number of people looking at Blackboard versus the number of people that come into the YouTube stream and the number of people that go to Pearson is small. So I'm going to continue to use Blackboard as a place to announce things, and I will put files, PDFs and files up there. But our main resources are going to still be Pearson as it was through the original design of the class, and then in the YouTube version of this will be the classroom on this. So let's go here. I wanted to get in. Let me put the browser window up. Oops, that's that. I want to go to graphs. I have the graph window twice. Let me fix this here. There we go. And now we have the Blackboard window. All right, so if we come over to Pearson and into what's showing on the Pearson portal, you can see that the homework is continuing to show with the due dates coming across. Working our way through chapter 4. The meat of the material that we're studying right now in chapter 4 usually takes a couple weeks to discuss and practice. And so these next 2 sections, 4 and 5, you will see kind of get sticky. And we hone into them a bit. So the homework, practicing the homework before and during the conversation is very, very useful to the detail of the stuff that we're looking at right now. And that did not switch over. Let's try it again. There we go. There, the Pearson finally came up there. So looking at this, on Pearson here, we are finishing the test on chapter 3. You should be wrapping that up this week. I have had the review questions, and I'll go show you what's up on the video section of this in a second. And we have been discussing lecture-wise during the course of last week and this week, chapter 4, with the homework due dates being kind of extended in the future. Now, the idea is I know people's schedules have, for some people, have changed. For some people have changed to where their times need to be flexible. So the due dates are in the future and the lectures are of the now, but I suspect a lot of people will be watching the lectures as they're working their way through the material, and the due dates are kind of when we want to end discussion on things. So that's where we are with the Pearson due dates. I will get the next exam scheduled in on chapter 4, and then we kind of wind down with chapter 5 that leads us into the final. So that is this. Let me get YouTube. And down here, for the life of me, I never understand why they suggest particular videos. I'm having a playlist where I store all the material that I gets recorded. The lectures will always be in the top if you come to the playlist, and the playlist is the link that I'm sending out. And then after the lectures, so today's evening lectures will go here after this, there are example problems that people have asked me questions about from the different reviews. Some people had asked me about these review question problems. Some people had asked me about completing the square. And so I put these different things up here. And then they're using Desmos to find extrema, and an example from the book on Torricelli's law and how that works with the polynomials we're looking at. So I'm going to continue to place things up here. The lecture is the main content, but there is additional material here. Generally, this is answers to questions people have asked me, and I'm sharing the answer for everyone, treating it as if someone asked a question before the class. And so I'm showing the specific examples in the video streams here. So you will want to check these if there's anything coming through. You're going to be seeing coming up shortly chapter 4, section 1, problem, whatever, based off the questions that people have asked in the homework as I do some example problems coming across. So that's where our material is. That's where we are with Pearson and the lectures and videos coming across. For people whose schedules are different, in that email I sent out, there are 4 times where lectures are. There's 2 lectures during a week, and the evening class had those kind of separated. The day was kind of separated in half. But I still have a morning class that has those lectures. You're free to watch, to come into any stream that fits your schedule. So we'll be breaking those through. And I'll probably repeat this every lecture coming across. It just feels comforting to repeat the same things over and over again. All right, so in the material we had worked with, we have been working on polynomials. So I'm going to start with the idea of a polynomial in one form, and we're going to kind of try to redefine the form as much as we can. And so the polynomial form we're looking at is, make sure I can see your comments off here, and please feel free to use the chat as a place to ask questions. It's amazing the difference between classes and how questions are asked, and you guys are quiet, while the day class asks a lot of questions. And well, it's personalities, right? No grouping of people are exactly the same. This is a general form of how we write a polynomial. Now, we want to focus on having our powers in descending order, and this lets us highlight the coefficients. And the coefficients are going to be the things that drive everything, and I'm keep hinting at that the constant and the leading coefficient really define the polynomial and will help us get clues to figure out things that come from these. And so n is the degree of the polynomial. And we worked with n equals 0, which are constants. N equals 1, which are linear functions. N equals 2, which are quadratics. Our job, because we have good definitions of these things, is to take for any high order n, so when I say higher high n greater than or equal to 3, and break it down into linear and quadratic factors. Now, so by saying linear and quadratic factors, I am hinting at that multiplication is a key of creating polynomials. And I hope we appreciate we saw this when we worked with quadratics, that if I had two linear factors and I multiplied them, I got a quadratic form. And we worked on going backwards and forwards, from starting with the quadratic and finding its factors, starting with the factors and finding the quadratic. Same thing's going to happen with polynomials, and that's why we started talking about division of polynomials. And so one of the things we want to work towards or look at is how we can divide a little more quickly. And so we're going to have a special case of division where we divide our polynomial by a linear factor. And so it's in the form of x minus k. Just like when we talked about the remainder theorem. The remainder theorem was if we're dividing a polynomial by x minus k, here, I'll put the remainder theorem over here, I'll put it in blue. All right, if f of x is divided by x minus k, then the remainder is equal to f of k. And the thing to note here is the negative sign. And so the same thing is happening here. We're going to be dividing by a linear first term, and has a negative sign, and so it pulls out. And we have a special way of dividing that's called synthetic division. But it only works if our divisor is a linear term. And so what we do to do synthetic division is we write the coefficients of the polynomial only for each term. If a term has a sub n equals 0, we write 0. Just like in the long division of polynomials, if we were missing a particular power of x, we would write 0 of x to that power. We write k to the left, we bring down the first term, bring down the first coefficient, and we multiply k times this number. Write the result under the next coefficient, add these numbers, and repeat. It's a repeating algorithm, just like the long division repeated until we were out of of terms, this is going to repeat until we're out of coefficients. The key is to watch your signs. We always get the signs odd because of this negative sign here. I'm going to do a few examples of synthetic division. It's going to help us for the thing that we do afterwards. Again, you can do long division instead of synthetic division. Synthetic division just runs a little bit more quickly. But if you're comfortable with the long division and you're okay with the little bit of time, take the little bit of time. So there we have this here. Let me find a good polynomial. All right, so I'm going to look at f of x is equal to, I'm going to make f of x equal to 2x cubed plus 4x squared minus x plus 5. And I'm going to divide it by, so f of x divided by x plus 2. So for step 1, I'm going to write my coefficients. 2, 4, -1, and 5. So there's step 1. I'm going to write k, which is -2, to the left. All right. I'm going to scroll down to step 3 because now I'm in the repeat mode. So, all right. So I wrote my coefficients, and I wrote my k to the left. Now I'm going to give myself some room, and we're going to bring down the first coefficient. So I'll draw a line here, and I bring down 2. Multiply k times this number. So I'm going to multiply times 2. So -2 times 2 is -4. I write that result here. So I do this multiplication, and the result comes over to the next term. I add these numbers, and I get 0. Now I repeat. So I come back here, and I'm now focusing on this multiplication. So I multiply k by this, and the answer goes here. So -2 times 0 is 0. And I add these numbers, and I get -1. And I repeat. So I multiply k times this number, and the result's going to go here. So -2 times -1 is +2. And I add these numbers, and I'm now out of terms. Now the thing I remember is twofold. This last number is the remainder. This number is x to a degree less than 1. So one less than the first term. So to translate this back into a polynomial, this is 2x squared minus 2x squared minus or plus 0x minus 1 plus 7 over the x plus 2 that we divided by. So this is the x squared term, this is the x term, and this is the constant. We get a power 1 less than what we started with, and so it divides down. This runs a lot more quickly than long division did, just space-wise. the remultiplying everything back out. This multiplication here, it focuses on leading terms and it pulls everything towards the end. It's really, really quick, but it is restricted that it only works if we're dividing by a linear term. All right, so let's look at a couple of these. I want to do a couple of these, and I want to do some with different terms in them. So I'm going to jump into the example problems in the chapter on page 299, and I think I'm going to look at number, let's see, number 40 looked good, but I think when I did this before, yeah, number 45 is actually an interesting one. So I'll look at 45 in the book. So I'm going to scroll up here, change colors. All right, so number 45 has x to the 5th plus x to the 4th plus 2x plus 2. And I'm dividing this by x plus 1. So if I'm going to do this as synthetic division, I need to write my coefficients. So I have 1 for the 5th power, 1 for the 4th power. Notice I have 0 for the 3rd power and 0 for the 2nd power, right? I have to do something with the x cubed and the x squared terms, but their coefficients are 0. So I have to make sure I bring down those 0 coefficients. Then I have 2x for the first and 2 for the constant. Now off to the left, I'm going to write my k term, but my k term is -1. Remember to watch your signs with these. You'll see why as we look at roots and zeros shortly. So I bring down my first term and I multiply. -1 times 1 is -1. I add this column and I continue my multiplications. And -1 times 0 is 0. I add this column. I get 0. -1 times 0 is 0. I add this column and I get 0 again. -1 times 0 is 0. I add this column and I get 2. -1 times 2 is -2. And I add this column and I get 0. And this was my remainder. The last one is my remainder. So if I look, this was x to the 5th. So this represents x to the 4th. This is x to the 3rd. This is x squared. This is x to the 1st. And this is the constant. So I have 1 x to the 4th plus 2. And so this synthetic division quickly reduced the terms for me here. All right, let's look at one more. And I think I'm going to do 48 in the book, because this uses a fraction, and this lets us see how fractions work. So we have x to the 4th minus 1/2 x cubed plus 3x squared minus 5/2 x plus 9/2. So I've got fractional coefficients, but that's okay. And I'm going to divide it by x minus 1/2. So for the synthetic division algorithm to work for me here, I need to have a linear term, and I do. X is to the 1st power. This is linear that I'm dividing by. So I need to write my coefficients for my polynomial. So I have 1, negative 1/2, 3, negative 5/2, and 9/2. And I'm just going to double check. I have 4, 3, 2, 1, 0 for my powers. So I have no hidden terms in my powers there, right? I have each coefficient takes care of every possible power of x for a degree 4 polynomial. Then in my k term, remember our signs here, is a positive 1/2. And so I now have this in a form that I can do my synthetic division with. So I'm going to bring down my 1. 1/2 times 1 is 1/2. I add these terms and I get 0. 1/2 times 0 is 0. I add these terms and I get 3. 3 times 1/2 is 3/2. And so 5/2, negative 5/2 plus 3/2 is negative 2/2, which is the same as negative 1. And then 1/2 times negative 1 is negative 1/2. And 9/2 minus 1/2 is 8/2, or 4. And this is the remainder. So this was a 4th power, or 4th degree polynomial. So this represents the x cubes, the x squareds, the linear x terms, and the constant. So I get x cubed plus 3x minus 1 plus 4 over this part, x minus 1/2. And so we're able to do our division, our synthetic division. Our key, as always, will be dividing by a linear term or a linear factor. And I want to transition this to that we want to start talking about why we have been dividing, and that we want to talk about the factors that build up polynomials. We want to look to how a polynomial is built from linear terms. And so I think the first thing the book does is it creates something called the factor theorem, and it's an extension. And I kind of went over this when we were talking about the remainder theorem. They're saying, hey, you have this remainder theorem. Well, a polynomial, f of x, has a factor, x minus k, if f of k equals 0. And it's actually if and only if. Right? If and only if f of k equals 0. So what this is telling us is that our remainder theorem, if I divide the polynomial by x minus k, for x minus k to be a factor, it has to have a remainder of 0. And this becomes a useful tool for us because it lets us check to see if particular numbers are factors, because we have an ability to check it. We have an ability to go back and check it. So let's look at an example here of a test. I want a positive test, not a negative test. So if I have where did my numbers go? 2 seconds. Go back to the problems at the end of the chapter. I can always grab one from there. There we go. There's the function. It was written down at the bottom of my notes. If I have a polynomial that is x squared minus 2x minus 3, and I want to know if x plus 1 is a factor. So to check this, I have to put in here -1. So -1 squared minus 2 times -1 minus 3. So -1 squared is +1. -2 times -1 is +2 minus 3. Well, this does indeed equal 0. And so this is a factor. So yes. And what's happening for us here is at -1, this parabola passes through the x-axis. It also passes through at 3. And here's the thing I want you to note. Notice x plus 1 is the same as having a solution of x minus 1. And how we build polynomials, they're built from multiplication. They're built from multiplying these roots or solutions or zeros. The places where f of x equals 0, we work on multiplying them together or as a list of factors. So the answer, x equals -1, is where we're actually getting this k value from. And so the thing that I will keep repeating, probably like 15 billion classes, we did this with quadratics. If I have a times b equals 0, then a equals 0 or b equals 0. And for higher order polynomials, I can have multiple things which says that any one of these factors equals 0. And what equaling 0 means for us graphically is we're looking at the place where the graph touches the x-axis or attempts to pass through the x-axis. And so each of those solutions come into becoming a factor. Well, watch how I can turn an answer into this form, into this factor. So if I'm saying x equals -1, if I add 1 to both sides, I get x plus 1 equals 0. And that becomes the thing I can multiply by. It's things that I can use to build polynomials out of. These solutions let me build the polynomials. And I can build the polynomials from it. So we kind of have to look at a couple of things that our polynomials do and what we can do with them. And the first thing I want to look at is called multiplicity. And it kind of has to do with the even and odd nature of a function. Just putting up an axis here. If I have a root, and we're going to say this is going to be -2. So this means that this polynomial can be built off of x plus 2. That's the factor that comes here. Now, if my leading coefficient is positive, and this function that I'm building is odd, then I start negative and I end negative. Odd functions with their leading coefficients move from one side of the x-axis to the other. So if I have x plus 2 to some power, and that power is odd, I cross the x-axis at that point. But if I have that power is even functions with positive leading coefficients, I'll make evens red. Even functions start at positive infinity and end at positive infinity. So they just touch at that. So let's look at two functions that have the exact same root, but they have different powers of those roots. And we call that power multiplicity. Sounds like the dog is not liking the family right now. And so we're going to look at how the multiplicity affects this. Let's come over to a graph here. Let me see if I can get my graphs up. Yep, that's not the graphs. There's the graphs. All right. So I'm going to clear these two functions. And what I'm going to plug in here is I'm going to take that x plus 2 that we had, and I'm going to raise it to the first power. And so right now it's a line. And this has the form of all odd powers. All odd powers with a positive coefficient start at negative infinity, and as x increases, they go towards positive infinity. So because of that, they have to cross the x-axis somewhere. As I can continue here, I'm going to use the same root, but I'm going to increase its multiplicity. I want to say, hey, this is going to be squared. A squared multiplicity or square-powered function comes down to that root from positive infinity, turns around, and goes out towards positive infinity. So I have an odd function and even function. Well, I'm going to do that for two more powers of this. I'm going to do this root. I'm going to give it a multiplicity of 3. So I take it to the third power. So notice it comes to the third power, or comes to the same root, but still leaves in the same direction. And I'll do one more to the fourth power. And I'm going to turn off the lower powers here. So a fourth power looks like a parabola. And so this multiplicity tells us how the function is acting at this root, at this solution. If it's odd, it punches through the x-axis. If it's odd, it punches through the x-axis and gets to the other side. If it's even, it bounces off of it. Well, doesn't mean that these can be even or odd functions. Let me take another root, x minus 3, and put it out front for this one here. So now I've converted this function, x plus 2, yeah, the brown, yep, thanks, Josh. Let me get back to here. Come down to here. Thank you. Where did it go? There. There we go. Okay. Let me repeat these here and show these back. My apologies there. My live screen was in the right place. All right. I'll go back through each of these and I'll repeat this. Thank you, Eric. Thank you, Josh. All right, so notice on the left-hand side here, I have the same root. If it's to the first power, it does what odd functions will do. Start at negative infinity and punch out at positive infinity. To do that, it has to pierce the x-axis. And first power problems are linear. If I take it to the second power, it becomes a parabola. So it starts at positive infinity, comes down to that root, bounces off, and heads out to positive infinity. And I'm going to turn off the first power, and I'm going to change it to a multiplicity of 3. So it's still like an odd function. It has to start at negative infinity and run off to positive infinity. So it's punching through the x-axis, but it has that little kind of inflection, that divot there. And if I look at a fourth power compared to a third power, it bounces off the root. It's just a little bit flatter near it. And so we call these powers of the root the multiplicity. And it's actually how many times that root is repeated in the solution. So this x plus 2 is a fourth order polynomial. It just has the same solution repeated for each of its roots 4 times, or a multiplicity of 4. And even though this has a multiplicity of 1, I can combine it with a positive 3. And so this has a multiplicity of 1. And this has a multiplicity of 1. These functions together have a total power of 2. It's degree 2. Can add up all my multiplicities. But because this solution is degree 1, I come into that solution, that root has a multiplicity of 1. You're punching through the x-axis, turning around and coming back out, and punching through the other one. So if I were to change the second one, x minus 3, to the second power, it's going to bounce off of it. I come through at x minus 2, x equals minus 2, which is this term. I turn around and come down to x minus 3, but because it has an even multiplicity, I bounce off of it. If I were to change this to an odd multiplicity, I'd bounce through it. Change it back to even, I bounce off. And so the multiplicity tells you how the root responds to being a solution. So here, if I continue the x minus 3, right, x plus 2 is even, so it's going to have to bounce off of it. Overall, my function has a total multiplicity of 3, so it's odd. I have a positive coefficient in the front, so I start at negative infinity and I end at positive infinity. So I come to my first solution, it has a multiplicity of 2, so I bounce off of it. Somewhere in between here, I have to turn around, and because my second solution, my second root, has a multiplicity of 1, I pierce through it. And so these multiplicities, this repetition of how often a solution appears in our answer tells us if, hey, that's an even multiplicity, right? And so that's x plus 2 to an even power because it bounces off the root. And that's x plus 2 to an odd power because it punches through the x-axis. So the repetition of these roots gives us a little bit of the behavior. What we get from all of these roots and all of these factors that we can put together is, if I have my polynomial of a sub n x to the n plus a negative 1, I will be moving out of the dining room, hence where the dog is, drinking from her bowl this weekend. I got the stuff to move out to the porch, and hopefully the weather is going to be warm enough that being on the porch won't freeze me to death. So hopefully we won't hear the dog drinking out of her bowl. I apologize for that. All right. You just assume it's like being in the classroom, someone wandering down the hallway, which happens periodically. It's okay, because I'm just writing our standard form of our polynomial again. And what we can do is we can talk about it being completely factored. We can get our polynomial to be completely factored so that we have the a sub n is still going to hang out in the front. This leading coefficient does not go away. It hangs out in the front. And then we get a collection of things we multiply by. And notice we're going to have n of them. And so these two things we can transform into each other. We can take this and write it in terms of each of its zeros, roots, or solutions that give us our factors. Because notice, if I have a whole bunch of things multiplied together and I'm looking for when f of x equals 0, then in each of these things equals 0. And I can find all the possible x values this polynomial will give me as a solution to an equation. And so this game, I just don't think she's used to this routine. Hold on 2 seconds. All right, sorry about that. The ability to get any or all of these factors can help us find solutions. And so our job is to use different tools to pull apart our polynomials. And the key tools that we're going to have are going to be division and the remainder theorem. But we need to find a way to find something to divide by, something to make these smaller. And so what we're going to have to do is come up with a series of tests that are going to help us find are our factors right or not. And so the first test that we're going to get to, the first thing that works us through everything here, is the rational zero test. Now, you're going to hear me, and you notice I use multiple words here. Roots, zeros, or solutions. This book tends to call them zeros, and they're the place where the function f of x equals 0. It means it's the place where it crosses the x-axis. And what we can do is this is where we can find solutions. We saw this with the quadratics. If we set up a quadratic equation and we set it equal to 0, we would get solutions at the place where it crossed the x-axis. Same thing happens with polynomials. We can set a polynomial equation equal to 0, and we can find all these places it crosses the x-axis, which will solve that equation. And so that's why I call them solutions. They've gotten the term root because it's the thing that you build the polynomial out of. We multiply all these things together. We get the polynomial to the root. And it's also called the zeros. And so really the roots and the zeros are x equals c1, x equals c2, x equals cn, right? Dot, 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 cn. But if I subtract cn and c1 from either side, I get my factors. And so we kind of have to think in the two spaces of, I can think about the x minus something that I'm multiplying by, or I can turn that into the x equals as a solution, and we just have to watch our signs. And that's why the remainder theorem and synthetic division and all of these things have the sign of an x minus, because these things are using the root and the 0, right, to make the factor or to do the factors. So it's a little bit of a language. It's a little bit of what side of the equation you're sitting on. And so the rational root test is how I always used to say it, but your book calls it the rational zero test. So I try to use the book's words when I can, though I try to point out different ones. I'm now very, very conscious of people going I wasn't sure how to do that. I want to look at Khan Academy, and Salman Khan's gonna say, hey, that's actually a root I'm looking for. Or you Google it and you go to Purple Math and they're saying, hey, I'm finding solutions. And I just want you to be aware that these terms are interchangeable. I think I am a root person. You'll hear me say root and factor a lot. In fact, when I'm thinking of division, I think of factors more than I think of the solution part for them. So we are going to have a polynomial. So we're going to say, and we're going to put a little restriction on this polynomial. This rational zero test, the rational root test, only works in a very specific condition. But it's a condition that we can recreate fairly easily. So we're going to say let f of x equal, and we'll write our polynomial in the form we've been writing it in. Whoops, get my coefficient in there. And a sub n cannot equal 0. Now, a sub n cannot equal 0, and all coefficients are integers. So we're not going to have fractions, we're not going to have decimals, we're not going to have pi, we're not going to have imaginary numbers. They're integers. Now, what's nice is if they're fractions, we can multiply by the denominators to get rid of the denominators, because these things are going to equal 0, so we're going to be able, or we could pull out, we could factor out the parts that are creating the fractions. And so a lot of times you'll see when we're solving equations, we'll get these to be integers, because this will help us here. And the fact that a sub n can't equal 0, all that's saying is, well, if this was a to the fifth and this was 0, well, then I really wouldn't be calling that a fifth order polynomial. I'd be starting with a to the a4, right, with the fourth order polynomial. So our leading coefficient has a value. And so if we have integer coefficients and leading coefficients, that if some rational number in its lowest form, so we've simplified it, right? We're not going to have 10/50ths. We'll simplify it to 1/5. So if P over Q is a 0 of the function, then P is a factor of a sub 0, and Q is a factor of a sub n. And so this is why I've been saying the constant and the leading coefficient are the things that are going to help us the most. And we solve this with quadratic equations. We had x plus 2, and 2x minus 1. And if I multiply these together, I get 2x squared, 4x, so plus 3x, minus 2. And so negative 1 was I'll actually do the 2. X plus 2 equals 0, so negative 2 is a 0 of this. So negative 2 is a root. And it happens that negative 2 over 1, well, negative 2 is a factor of the solution, and 1 is a factor of this coefficient. So in quadratics, we saw this. This is actually kind of how the AC method worked. We were able to slide the one thing back across, and we could pull the factors out, and we could say, hey, if these factors of this number do this, then they're part of our solution. Well, now we're going to be able to do this for higher order terms. We're going to be able to do it in a way that's going to help us solve things. And so I'm going to work through a couple of these. We're going to get this rational root test down. We're going to probably do 2 of them. But one of the things that happens is the larger your leading coefficient and your constant are, or the more factors they have, I guess, because they could be prime, but the more factors they have, the more possible solutions you have. And so what this test does is it lets us find possible solutions. So let's use this. And possible solutions help us get away from not knowing where to go with something to making the problem easier. I'm going to start a new page here, 2 seconds. All right, so I'm going to go a little bit blue here. Let's look at the polynomial f of x equals 6x cubed minus 5x squared minus 7x plus 4. Looking at this, I actually don't know much to tell you about it. I know I've got a positive a sub n, so there are some behaviors I could pull out of this in how it's coming in and going out of the function. It's a 3rd degree polynomial, so it's going to be moving generally in this direction, starting in negative infinity, working its way out. Having a 3rd degree polynomial, I have a possibility of having 3 solutions, but that's about it. I'm not sure where they are. I don't know how big they are. There's a lot going on here, but I'm going to use the rational root test to help me dig out of this, and I'm going to make this problem easier. And so my goal here is I want to find at least one root and make this problem easier. So I'm going to use the rational root test and the remainder theorem to do that. So I'm going to list let me see here. Going to list my factors of my a sub 0. So a sub 0. Now in your book it's saying that's p. P are all the factors of a sub 0. So my possible factors of a sub 0. Well, I can have 1 times 4, and I can have 2 times 4. But I can also have negative 1 times negative 4, and I can also have negative 2 times negative 2. So for all of these, I get the plus or minus. All right. So for all the factors of 4, I have my positive versions and my negative versions. And so that's possible p's. All right, we got to mind our p's and q's here. All right, for the q, I need all my possible factors of 6. So again, I'm going to keep the plus and minuses because they're plus or minus 1. And plus or minus 2, which is times 3. And that 1 in the front was times 6. And so there are all the possible factors of p and q. Okay, so I have to now write all the possible. Notice the word possible dominates here. possible combinations of these in a fraction. And so my possible p over q, where q is my denominator. Now what's nice is all of them get a plus or minus. And you can just keep this going through. So the first denominator I can get is going to be 1. And I can have 1 over 1. I can have 2 over 1. For each q, I'm going to list every p. And I can also get 4 over 1. So I've worked my way through the first possible denominator. Second possible denominator is 2. So I get plus or minus 1 over 2, plus or minus 2 over 2, and plus or minus 4 over 2. And so I've gotten rid of half of my denominators. Now I'm halfway there. All right, let's look at that as a denominator, 3. So I can have 1 over 3. I can have 2 over 3. And I can have 4 over 3. And my last denominator, which is 6. So I can have 1 over 6. I can have 2 over 6. And I can have 4 over 6. So these are my possible zeros. Well, let's see, what do we have? 1, 2, 3, 4 times 3, so that's 12, plus there's a plus or minus, so I have 24 possible solutions. But I want to clean this up. So what I'm going to do, 1 over 1 is 1. 2 over 1 is 2. And 4 over 1 is 4. Then I'm going to have 1/2. But notice 2 over 2 is 1. And I already have that, so I'm not going to write it again. 4 over 2 is 2, and I have that also, so I'm not going to write it again. And plus or minus 4/3. So I've worked my way through here, and I'm going to look at these last ones. Plus or minus 1/6. Well, 2 over 6 is 1/3, and I already have that. And 4 over 6 is 2/3, and I already have that. So I've reduced the amount of possible roots I have. And these are all my possible solutions, if it has a rational solution. But we went from this, where we don't have any idea of what the answer is. At least I don't. I have experience with these things. I've been doing this particular decomposition of these things 10 years. And when you look at them, there are some patterns that come out, especially if you're missing things in the middle. But in general, I could not tell you where about this would be hitting the x-axis. A small change to some of these middle coefficients can really, really spread things out and change things on how it moves up and down. The ratio between these two things spread them all out. And so taking this, leading coefficients factors and the constants factors, gives us an anchor point. It gives us something that we can kind of crack into and see. And these are our possible solutions. So I'm going to write the function now down here. So 6x cubed minus 5x squared minus 7x plus 4. Well, we have the remainder theorem and the factor theorem to help us out here. And so if any one of these, if I plug them into here, equals 0, it's going to be a factor. So what I'm going to do here is I am going to plug in 1, because I like 1. All right? 1 into any of these numbers is 1, so it gives me the coefficients back. But I like that. That makes the calculation a little bit easier. Right? 6 minus 5 is 1, minus 7 is negative 6, plus 4 is negative 2. So 1 is not a root. The remainder theorem tells me, hey, I have a remainder. This is not a root. It's not a solution. All right, well, I'll try negative 1. So negative 1 to the third power is negative. So it changes my sign to negative 6. Negative 1 squared is positive, so that leaves the sign the same. Negative 1 here would be negative, so negative times a negative is positive. And that stays positive 4. So negative 6 minus 5 is negative 11. Plus 7 is negative 4. Plus 4 is 0. And I found one. Negative 1 is a root. It is a solution. Now I know, because this is a third degree polynomial, I have up to 3 solutions to look for. Now I could go through and I could try each one of these into the remainder theorem to see which ones equal 0. And I know on this problem I will eventually find all of them. But there's actually something that we can do that reduces this problem. It makes this problem similar to things we had done before. In fact, I'm going to take this and I want to turn it into a quadratic. And then I'm just going to use the quadratic formula, because we spent a lot of time learning it, because it's a lower degree problem. It becomes a little more tractable. And so I'm going to, and I'm even going to use synthetic division to do it for me. So I'm going to write the coefficients of my polynomial. I'm going to write my k, which is the root, out here. And I'm going to do my synthetic division. So I'm taking this larger problem, and now that I have found one solution, I'm going to make it into a smaller problem by dividing by that solution. And so what I'm dividing by is x plus 1, because x plus 1 as a factor is equivalent to my answer being x minus 1. And synthetic division says, hey, I take the opposite of the sign, or I take the root. So let me pull this up here, and I'll do my synthetic division. So I bring down my 6. Negative 1 times 6 is negative 6. Negative 5 and negative 6 is negative 11. Negative 1 times negative 11 is positive 11. Negative 7 plus 11 is positive 4. Positive 4 times negative 4 is negative 4. Add those and I do get a remainder of 0. And this is my simplified polynomial. I have 6x squared minus 11x plus 4. And so I can put this into the quadratic formula to find my other roots. So a equals 6. So I don't have to switch the sign if I'm talking about it as a root. So, and this comes in. So Josh asked off on the side of the chat here, do you still switch the sign to make negative 1 when using the root? The rule is if you're dividing by x minus k, you use in synthetic division, you use the k, and that's because of the sign there. Well, if I have x minus k equals 0 as what defines a root, then my root is the k without the sign switched. So when I get a root, I keep the sign. When I have a factor, the sign switches. Root, keep the sign. Factor, sign switches. And yes, I mess up signs all the time. This is one I have to talk it out. I have a tendency to work from roots more than factors. I've been talking factors a lot because that's how we discussed them in the first few sections of this. Now that we're getting them into solutions, we're more into the way I'm talking. So I don't see this as switching a sign. I see it as using the root as it is. And synthetic division is really designed to use the root. And c equals 4. So on my new, let's see, I'm going to have -6 plus or minus -11 squared, which is 121, minus 4 times 6 times 4. Am I missing a sign on any of that? Nope. Over 12. So calculator. Right, because what was it? What is our quadratic formula? -b plus or minus b squared minus 4ac all over 2a. So, oh, no, that's not -6 out there. That's +11. Glad I wrote the formulae there. So positive, let's see, -b is +11. -11 squared is 121. Minus 4ac is minus 4 times 6 times 4, all divided by 12. So let's get what's inside. Let's get our discriminant here. 121 minus 4 times 6 times 4, which is 25. So this becomes 11 plus or minus the square root of 25 over 12. And so that's 11 plus or minus 5 over 12. And so our two answers, I'll put 16 over 12 and 6 over 12. And so 16 over 12 is both divisible by 4 4/3, positive 4/3. And that's 1/2, positive 1/2. And let's look. They were there. There's 1/2, and there's 4/3. And so my solutions to this thing are -1, 4/3, and 1/2. That's the same as writing the factors x plus 1, x minus 4/3, and x minus 1/2. And if you were to multiply all these together, you could get the polynomial. And so let's take this all the way back to our polynomial formula. Which said that we could write it in a complete factored form as a sub n times x minus c sub 1 times x minus c sub 2 times x minus c sub 3 in this case, because there's 3 of them. And so a sub n in this polynomial was 6. And that is my completely factored form. So we're able to break down, we're able to find solutions, because these things work to solutions, and we're able to completely factor them. And the key, our key point to all of that are our P's and Q's, our leading coefficient, and our constant. And if we multiply all of these together, the last thing will be a number without any variables. So it'll be submultiplication of these 3 things and that leading coefficient. And so these things all combine coming back. All right, so this is one test. One entry into solving. Well, you heard me say, hey, you know what? I could have three possible solutions. But I keep using this word possible. And so we're going to want to find out what this means and what we can do with it. And so the next test we're going to look at is Descartes' rules of signs, and then we're going to look at the fundamental theorem of algebra to put it together. We're going to take a short breather for this. This really is the key to the first lecture. And so let's see, it's 7:15. We'll say around 20 of 8. We'll come back in here. Everyone get a break, stretch their legs, use the restroom. I'll send out the new stream, clean up, and then we're going to look at the rest of section 4 and most of section 5. We're going to start putting all this stuff together, but this is really the work we're going to continue on. Is we now know how to divide polynomials, we know what polynomials are, we know how to find their extrema on graphs, and now we're going to do the work of using this division to find solutions. And then once we have that tool, we'll go, okay, well, what does that look like in the real world? That's not all tonight. Tonight we'll get the tools set up for finding solutions. So any questions short term, fire them off in the chat here. I'm going to pause everything out and around 20 of start a new stream.